Hello, I'm Mark Claypool. I'm a professor of computer science at Worcester Polytechnic Institute. It's a school in Massachusetts near Boston. Did this work with Shengmei Liu. She's a PhD student of mine, also at WPI. We'll talk about EvLag. It's a tool for monitoring and lagging Linux input devices. So latency degrades interactivity for computer applications, whether it's your touchscreen app that you're playing on your iPad, particularly so but for games. So games are highly interactive. So you provide input often, rapidly, many kinds of actions. You respond to the output. And the player performance matters. So players care a lot how they do. It can make it less fun when there's latency in it, and it impedes your interactivity. There's techniques to mitigate latency. So latency compensation, they're called. But in order to use the right ones and to use them in the right time, we need more studies. So more studies of games, more studies of game actions. So typically such studies are done by a user study, where you set up a system where we can add latency to the interactivity. The user can play a game, some sort of interactive game, small application, and Proctor, the user study researcher, will measure performance or the quality of experience, change the latency, and repeat. So that's a typical process. So what this means, though, is sort of depicted here in this case, is that way we have the ability to add lag. And that usually means you take the game and you have to modify the code to put it inside the game, or maybe the game engine, right? So that means there's a limited set of applications we can test. So the game is usually open source, or there's sort of these toy applications, or there's something that we can build. So we can't actually use commercial games in that case. In addition, you have to re-implement the code every time. So every game and every system, you have to re-implement yourself. That means there could be bugs. So an alternative approach that we're trying for is to let us run with any commercial game, in this case, Counter-Strike. And so we have the same input devices. And what EvLag will do then in this case is add latency in between the operating system and the device. So that is latency here, which lets us run latency studies with commercial games, let's say Counter-Strike. And so that's EvLag. It sits outside of it, lets us use commercial games, lets us add latency to any device in Linux, and also logs the input events. And that could be useful for a research study where you want to mine what maybe the actions are that the player did after the fact. So that's what this paper is about. Mention some of the features, talk about the implementation, a bit on the evaluation and use. All right, and this is an outline. I just sort of did an introduction here. I'll talk a little bit about related work. You'll see the paper for more details. And then go into the implementation, and then how is EvLag working? I'll show you a little bit about its use, so you can see, oh yeah, it's been used in some studies, and what can we do about it? And plus, there's a demo, and then I'll sort of conclude and summarize the end. So there's a couple different areas related to work. One is you talk about tools to add latency. There's a bunch of network tools that do this. If we use these for some of our studies, this is just a small list. Things like DummyNet, an older system, Clumsy, Mahi, NetM, just a small set of those. And again, they add latency to outgoing and incoming packets. So good for network latency studies, but they can't be used really for local latency. They don't affect your mouse click to screen render for a local system. There are a bunch of studies that actually have studied local latency. A list of some of them in this paper. Cloud-based game systems as well. They have a network latency, but they act a lot like local. And they all use pretty much the same technique I described, which is the modify sort of a small game, sort of a toy game, and you add latency to it, and we do it in the user study and see how it works. So again, typically not sort of a commercial game for that either. One important part is how to measure local latency. Is another area related to work. So how do we even know what the local latency is? There's different techniques, papers that have talked about those, from building sensors, oscilloscopes, cameras. We're going to use a camera-based technique that we've used, that others have used, and I'll talk about it in this talk to verify the EvLag is working. So an overview then for what EvLag does is it provides fixed latency for any Linux input device. You can actually lag more than one device at a time, so you can lag the keyboard and the mouse. And you can actually log the input events, one file per device for post-running analysis. It's implemented using Linux evdev, which is generalized raw input as character devices. So you can imagine the low-level input of a device that comes out is really nitty-gritty grungy, but evdev lets it look like a character device, and you can kind of read it, if you will, as a character device, as a file, if you want to think about it that way. Dev input with a bunch of different input devices there. The EvLag implementation, we use 3 threads, a reader and a writer, and a main. The reader and writer handle the events. The main is sort of handles the timers. I'll talk about each of those a little bit. So this is the reader thread pseudocode. Might be a little bit small here. I'll just talk you through it. Basically loops forever. Basically, it's going to read from the device, the evdev device. It gets the event. It says, hey, what time is it now? And then what time is the event queued? And it adds whatever delay you want. So it adds the lag to it. And then it puts it in this FIFO queue. And it repeats, gets the next event. So it's basically grabbing the events, adding the necessary lag to it. The writer is the thing that pulls from the event. So it checks has the latest event. It says, oh, is it time to dequeue that? Has the time expired, the lag time expired? If so, then it writes it to the device again, so the device the application can grab it and do whatever it's supposed to do with it. So it uses the same queue for that. It then blocks because it gets interrupted by the main thread. That's the timer. So it's going to pull from that queue at a rate that's controlled by the timer. And the timer is handled by the main thread. And the main thread does that. It uses the Linux RTC, the real-time timer, with a certain polling rate. And so the polling rate just lets it, so you're not busy waiting on it. You're actually mostly sleeping and still getting good fidelity on the timer. For each device, it sets up its own FIFO queue. Every device has its own. And then what it's really doing is it's getting interrupted by the real-time timer. And then it's waking up that writer thread. So it decides if that writer thread has an event to dequeue or not. Okay, so that's a high-level view. You can look at the Git repo for this if you want to look at the actual code. This is sort of pseudocode for what it does. This shows the example of the EvLag usage. So those are some of the options. So you can specify the buffer size. The default works well for almost all cases. This is the device you want to read. You want a lag. That's the device name, the dev input event. Yeah, you can log to a file as indicated. This is the polling rate that you might want. And then that's how much lag to add in milliseconds. So as an example, you'd run it this way. You have to be root. So administrator privileges to run. So that's my sudo. I'm running EvLag. I'm giving it 75 milliseconds of latency. The device in this case is dev input event 10. So it might be the mouse. So this would add 75 milliseconds of latency to every mouse event. So EvLag comes with some utilities too that can be useful for doing experiments or analysis. EvParse takes the log files, which are these character level input codes, and it parses them into something a little more readable. Two examples here. So it gives you the time of these two actions. And this is a mouse event. And it's relatively the X moved 1 pixel over, it's horizontal, and the Y, the next one, Y moved up -6 pixels. So you could process that. You can get mouse movements out of this. This is another event, keyboard event. In this case, the enter key, and the enter key is pressed down. Right. So this is another utility comes with is evdetect. You can appreciate if you take an input device and you plug it into a different USB port, it might have a different event number. If you have a script that automatically does this for your experiments, it can break, and it happened to us and so on. So this is just a script that uses evdetect to actually grab uses evdetect as a script to match a string, find out what input device it is, and then it gives you the input device number. So it can be useful for automating some utilities. So they come with the repo. Okay, so that's a bit of implementation. Again, details in the paper or in the repo. I'm going to talk a little bit about evaluation, see how well EvLag works, and then its use, and then conclusion. So in order to assess how well it works, I want to know, does it add the amount of lag we want it to? So we have to be able to measure the local latency. So we use a high-speed camera technique, where the idea is you take a high-speed camera, put on a tripod behind the user, filming the screen and the input device. High speed in this case is 1,000 frames per second. So I'm getting a frame every millisecond. And so now the user, when they go to click, in this case on a menu item, we can see when the click happens, and we can record the frames. So we're recording throughout. We can look at the frames and find out when the mouse is clicked. Then we observe manually, visually, when does that input show up on the screen. So in this case, there's a selected item. So we can count the frames between when it was selected and when it was clicked, and subtract the two, and you get the local latency. Right, so we can use this on our system, get the base latency without EvLag, but we can also use EvLag now and see if it's adding the expected amount of local latency. So this graph depicts the results. So this is the amount of latency I'm going to add on this axis, with this first case being the base system without EvLag running. And so this is the local latency measured. And what we did is we measured the average of 5 runs. So we did 5 of them. We compute a confidence interval for those values. That's that bar. So the base system we have is 25 milliseconds of latency, shown by that dot with a confidence interval around it. And then so that horizontal line is the base system. So now if I run EvLag, I want to see what it's doing. In this first case says, well, what is EvLag doing just running, right? Is it interfering? Is it adding latency because it's adding overhead? So this is EvLag with no added latency. And you can actually, the mean is actually a little bit lower, but those confidence intervals overlap. I mean, so EvLag by itself as overhead is not adding substantial amount of latency. Latency measured is the same. And then we can look at this point is 10 milliseconds of added latency with EvLag. That point is 50, again, shown with a mean and confidence interval, where that yellow dashed line is how much I might expect to observe. And you can see, again, that those points follow that line pretty well within the confidence interval. It suggests that EvLag is doing a good job of controlling the latency that I want to add to the input events. We've also used EvLag in a couple of studies, and this is one of them. This was a paper that appeared at ACM Chi, this last year's Chi, where we studied the effect of local latency on competitive gamers. In this case, Counter-Strike. So again, a black box, don't have the source code for Counter-Strike, want to use as an application, run the user study and see what latency does to those players. So these are competitive players are going to care about performance and how does latency affect them, and in particular, high-end gaming systems versus slower systems. So we had 43 users play it. And again, this is sort of the range of possible latencies in the system you might see. So gaming systems down on this end. So again, a 25 millisecond, that's a decent latency for a gaming system. And they might range, actually, we've measured some systems, they kind of go further than that. But, normal PCs can go in even hundreds. Actually, your consoles and TVs with the game engine, they can be even in the 200s. They can be really high. But in this case, we're using EvLag to control, again, from the base system, we can add lag. We can see over this range, what does that set of latencies do to the player performance and quality of experience, you will, but performance, and what I'm going to show you quickly. And, if you're a competitive player here, how much would you gain from upgrading to get a lower latency system? So this is a graph showing those results. So again, down here is my total local latency. And so my base system is 25. And what I've plotted here on this axis is the score. So you can look at, that's the score. So that's the average of those users at that latency. At this point, number of kills plus assists. And so, 57-ish points. And so there's a confidence interval around that mean. And then now this is adding 25 milliseconds of latency with EvLag, 50 and so on. So this is adding latency with EvLag so that it's getting more lagged. And so this is what's happening. The score is degrading, kind of a reasonable linear fit with that. And on this axis is improvement. So if you had this 125 millisecond system, and if you're a competitive gamer and you upgraded to a newer system at 25 milliseconds, your score would improve by 10%. And that might be a significant improvement if you care about your Counter-Strike score. All right, so this is one example of EvLag use. You can try it yourself. We provided a demo image for this paper, for this work. Link above my webpage, you can find the paper. It's a virtual machine, download it, the instructions to do so, has Linux and EvLag installed. You run a paint application, you paint on the screen with different amounts of latency. You can kind of feel how it looks, and it kind of walks you through that. Oh, this feels really laggy. And then you can look at the log files too. So you can try that out. Okay, so summarize. So understanding latency is helpful for designs and techniques to compensate for latency. Most user studies without EvLag have to modify code, kind of limits their use. You can't use them for commercial games, might be more bugs. EvLag adds latency to input devices in Linux, so it can be used for any application. Commercial games, sort of our target. Also logs input for post-analysis. Download it. Again, there's for Linux, we have an apt package, and so apt install package. Instructions on doing so right there. Same web page with the link. Git repo is also available as a link, so you can download open source, download it, modify it, take a look at it. In fact, some of the open source is useful because we have some additional features that maybe somebody else wants to add, but they'd be useful. So enhanced parsing of logs, so that maybe we could do something with game controllers. We could add a different amount of lag for each device. Right now, the same amount of lag has to be added for each device, but we could add a different amount. That could be neat. We want to do more studies, of course. So it's available for studies, ours and others, different games, different game actions, different input devices. And then it is Linux specific, which means we're limited to Linux-based applications. You can imagine it's not now extending the code. This is another application, but doing something similar for your platform of choice. Okay, thanks for tuning in. Happy to answer questions and talk with people. Definitely check out our paper and our website for more details. Thanks.